Can you see the presentation slide?
Yes, sir.
Okay, so today we shall continue whatever we have started in the last class. That is the topics on simple algorithm, semi-implicit method for pressure-linked equations. That is the primitive variable approach through which one can solve Navier-Stokes equations. That is whether it is a two-dimensional problem or whether it is a three-dimensional problem. So one can solve both two-dimensional or three-dimensional Navier-Stokes equation for the fluid flow problem by using that simple algorithm that is primarily based on the primitive variable approach. So also we have discussed the staggered git. I mean, if there is an issue with pressure velocity decoupling, so there is pressure and velocity are decoupled, and also we have proved, also we have shown for the pulsating pressure gradient situation when there is a zigzag type of pressure distribution, one may get an uniform pressure or pressure will not be considered at all by the numerical simulation. So under that consequences, to make the pressure velocity coupling to happen, staggered git approach is generally used, and that is basically employed in the simple algorithm for the numerical solutions of the Navier-Stokes equation for the fluid flow problem, which is the fundamental building block of computational fluid dynamics. So in the computational fluid dynamics, primarily everywhere for the solution of Navier-Stokes equations, simple algorithm is used. That is the only algorithm which is used for the solution of Navier-Stokes equations. Whether you are using finite difference method, whether you are using finite element or finite volume, whatever the method may be, could be, we always use simple algorithm for the solution of the Navier-Stokes equations. That we have discussed, and also we have derived the sets of equations for the solution of Navier-Stokes equations, and for the numerical solution of Navier-Stokes equation. That is, there are certain steps associated with. One is predictor step. In the predictor step, we basically predict the velocity. Once the velocity is predicted, that is u star and v star for the two-dimensional case. With the predicted velocity, we obtain the pressure correction equation, that we solve the Poisson equation for the pressure correction. Once the pressure correction equation is solved, then we correct the velocity. That is basically predicted and corrected. The predictor step, we predict the velocity and solve the pressure correction equation. In the corrector step, we correct the velocity and pressure from the predicted velocity of from the predicted velocities and the pressure corrections. And again, we repeat the steps till convergence is achieved. That is the till mass convergence, or we can say till the continuity equation. That is till the mass. That is a continuous satisfaction of the continuously satisfying the continuity. The continuity must be satisfied. So in order to obtain the mass balance, the mass has to be balanced. So in numerical solution, we also balance the mass by continuously satisfying the continuity. That is the primary consideration of simple algorithm or any solution or Navier-Stokes equation through the primitive variable approach. That part already we have discussed in the last class. Today we shall continue our discussion for the with the discretization of the governing equation. So how one can discretize the sets of governing equation using the simple algorithm and in the staggered git technique or in the staggered git approach. If we have a staggered git, how we can discretize the sets of governing equation that we have obtained for the simple algorithm from the simple algorithm. Now, in the staggered git, there are 3 grid points. That is, instead of putting all the grid points, all the variables in a single point, we decouple the velocities and pressure in a way such that at the center of the cell, if this is your cell, the center of the cell is your pressure, which is at ij grid point. Face of the cell is your velocity. So somebody is trying to enter. Yes. So at the face of the cell, this is the face of the cell. You can see this is the face of the cell. So we are basically this is the face of the cell. This is the grid point for the pressure, which is ij grid point. P ij. These are the grid points for the velocities. Black grid point corresponding to the pressure corresponds to the pressure grid point. Red grid point corresponds to the u velocity because it is in the x direction. U velocity, which is at I plus half j, and pink grid point, it corresponds to the v velocity, which is I j plus half. So I plus half j for the u velocity grid point, I j plus half for the v velocity grid point because v velocity is acting on the vertical direction. This is the direction for the v velocity, the direction for the u velocity, and this is the direction for the pressure grid point. So with this grid points that already we have discussed in the last class, that is we call staggered grid points. Velocity and pressure grid points are not at the same location. Rather, velocity and pressure grid point at the center of the cell. Velocity grid points are the faces of the cell. So this is a phase grid point for u velocity and a phase grid point for the v velocity. So we shall proceed in discretizing the governing equations or discretizing the numerical equations, which is basically employed, which is primarily employed for the solution of Navier-Stokes equation by using the simple algorithm, semi-implicit method for pressure linked equation, semi-implicit method for pressure linked equation. So this with the simple algorithm, we move forward in discretizing the governing equation with the staggered grid approach. So in the staggered grid approach, we will discretize the governing equation. Now let us start with our predictor equation. So in the x momentum equation, we have a predictor equation of the form that is u star minus up by delta t plus u del u del x plus v del u del y at p plus 1 level, 1 by rho minus 1 by rho del p star del x p plus 1 level into nu del 2 u del x2 plus del 2 u del y2 at p plus 1 level. Okay, this is the predictor equation for the x momentum equation. So u star is the predictor velocity, u star. Now, if we want to discretize this equation using the staggered gate approach, so this because since it is a u momentum equation, the discretization has to be made corresponding to the u grid point, that is at I plus half j grid point. This is the I plus half j grid point where discretization has to be made. So that's why I have written u star I plus half j minus up I plus half j by delta t plus u del u del x plus v del u del y, which is at p plus 1 level, that's current time step level, at I plus half j grid point, because since it is a u momentum or x momentum equation and we are discretizing the equation at the u grid point, so that grid point has to be satisfied with the I plus half j grid point. So this u momentum equation, since it is a u momentum equation, so we need to discretize at I plus half j grid point. So u star I plus half j minus up I plus half j by delta t plus u del u del x plus v del u del y I plus half j equal to minus 1 by p del p star del x p plus 1. But since p, pressure and velocity are coupled with the simple algorithm, although while discretizing the momentum equation, we are putting the grid point at I plus half j grid point, pressure will be always at ij grid point. So del p star del x at always at ij grid point. Del p star del x at always at ij grid point plus mu del 2u by del x2 plus del 2u by del y2 p plus 1 at I plus half j grid point. Is that clear to everybody? Please let me know if you have any doubt. Is that clear to everybody?
Yes, sir.
Sir, U
Okay.
star is base velocity.
Phase velocity. U star predicted velocity.
Okay, then how it is selected?
Last class you have not attended? Have you attended last class?
Sir, I did not attend, but I saw the lecture.
Sorry?
I have watched the recording of the lecture. I did not attend it.
The last class you are not there, right? Rupayan? Last class you are there?
Sir, in the last class I was not there, but I have watched the recording of the lecture.
Then what is U star here? What is U star here? Tell me.
Sir, U star is the star velocity. I mean the constant velocity. I mean
Is
U
that
equals
constant
to.
velocity? Is that so? No. You have not understood that. It means you have not understood. So who can answer this question? Deep, what is U star?
Sir, I had.
You have not
Hello.
also attended the last class?
No, sir. No, sir.
Deep?
No, sir. No,
Okay.
sir.
So who
Couldn't.
can answer this question? Who can answer this question? Shivnath, what is U star?
Uh, so actually, we have
Yes.
to predict
Uh,
the velocity U star from the
hmm.
guessed value of the P star by this step.
Very good. So U star is the, what is U star then?
So U star is the predicted
Predicted?
velocity. Velocity.
Yes. Okay. Now you have understood, Rupayan?
Yes, sir.
Okay. So U star is not a constant parameter. It is a predicted velocity. So basically, we are predicting the velocity at all the grid points, and from that prediction, we are in the next step, we are correcting the velocity. That is called the prediction correction approach. Simple algorithm, it is based on the prediction correction approach. Initially, we predict the velocity, which is not constant, which is basically we are predicting by solving the Navier-Stokes equations in the predictor step. So this is your Navier-Stokes equation. This is your Navier-Stokes equation. We are discretizing the Navier-Stokes equation. We are discretizing the Navier-Stokes equation. Discretizing equation, and we are predicting this velocity by solving this Navier-Stokes equation. So it is not a constant parameter. This is a variable parameter. This is a variable. We are predicting this variable or predicting this velocity parameter U star by solving this Navier-Stokes equation at I plus half j grid point. Is that clear now to everybody? Because this is a very important step.
So
If
one
you have
question.
any doubt, please. Yes, yes.
So we're discretizing the velocity at I plus half j points and discretizing the pressure at ij point. And
Yes, yes.
doesn't it make the equation inconsistent?
No, it is not making. That is a simple algorithm. What is that? We call it pressure velocity coupling, right?
Yes, sir.
There was an issue with the pressure velocity decoupling.
Yes, sir.
So pressure has to be discretized always at the cell center, ij point.
Yes, sir.
Whereas velocities are to be discretized at I plus half j point. That is not a discontinuity, because in the staggered gate, what is the staggered gate? Velocities are specified at the cell faces.
Cell
This is
faces.
the face, and pressure is the cell center, right? So since we are discretizing the velocity at the cell faces, that is I plus half j grid point, pressure has to be discretized at the ij grid point, because pressure is specified at the ij grid point only. That's why velocity and pressure are coupled. There is no issue with the decoupling. Okay? They are adjacent to each other. Is that clear now?
Yes, sir. So another thing, why don't you discretize pressure also at I plus half j and use an interpolation scheme?
No, you can. That is also a very good question you have asked. Actually, uh, initially the simple algorithm is made in such a way that pressure has to be discretized at the ij point. If you make that, if okay, let me explain further. If you consider del p del x, del p star del x at I plus half j grid point, then you will face the problem of pressure velocity decoupling. That is, that if there is a zigzag pressure will be cancelled out.
Okay.
You can try it. You can try it. There's a very interesting thing. You can try it. You'll find it that you'll face the similar consequences that we face when if you consider all the velocity values and pressure values at the same grid point, right? If we consider velocity and pressure values at the same grid point, then there will be an issue of zigzag pressure. So if there is an issue of zigzag pressure, then what will happen? Del P del X term will be automatically zero if there is a zigzag pressure. If there is no zigzag pressure, then there is no issue. But in reality, there may be a pressure fluctuation or pressure pulsation. So if there is a pressure pulsation issue, that kind of, if you consider del P del X and if you discretize del P del X at I plus half the grid point, then you will find that del P del X star will be automatically zero. That you had that problem that you had faced of taking all the variables, pressure and velocity at the same grid point.
Okay.
Okay.
Yes.
You can try it. You can try it. You will find the similar thing that pressure del P del X becoming zero if you consider this del P del X time at the I plus objective point. Any other questions from anyone? Okay. Fine. So let me proceed to the next slide.
Yes, sir.
Okay. Okay. Good. Now let us do one by one. Let us start discretizing because this is already fine. This is temporal discretization. Now let us start discretizing this term, convective term, u del u del x plus v del u del y at I plus half j grid point. How it is coming? So u del u del x plus v del u del y at I plus half j grid point. So it can be written as del u square del x plus del u by del y. Am I right? Am I right? Can I write u del u del x plus v del u del y as del u square by del x plus del u v by del y? Can I write it?
Yes, sir.
Okay, how can I? Can you explain on my behalf?
सर 2u del u del x हो जावे with the differentiation partial derivative
And then
del u square then it's I mean the del u square by del x is equal to 2 into u into del u del x or del u v del y. But after simplification we will get the same thing actually. That is what I'm trying to say.
then you need to apply some another equation after simplification. Where simplification of this expression del u square by del x plus del u by del
Sir,
y, while simplifying.
the continuity equation.
Very good, very good. Continuity equation need to apply. So this is right? This is right then. So del u square by del x plus del u by del y, I plus half j. So you can write this expression as like this. So that then you can write that del u square by del x I plus half j p plus 1 plus del u by del y I plus half j p plus 1. Right? This is the p plus 1 term you can write. Now let us start with the del u square by del x or I plus half j. Okay. Let us start with del u square by del x at I plus half j. So this I plus half j, you can write u square I plus half plus 1 j. Central differencing we are doing u square I plus half plus 1 j at p plus 1 level plus u square I plus half minus 1 j by 2 delta x. Right? You can write it as I plus 1 minus I minus 1 by 2 delta x. Is that okay?
Yes, sir.
Okay. That means u square I plus 3 by 2 j p plus 1 level minus u square I minus half j at p plus 1 level by 2 delta x. Fine. Now, can you tell me whether I can get I plus 3 by 2 j and I minus 3 by I minus half j, because are these variables at these grid points are defined? So whether these grid points are exist in a staggered grid thing? Can you tell
Yes.
me?
Yes, sir.
Yes. So okay, so that means these grid points are available, right? So somebody wants to enter. Yeah. So all these grid points are available in the staggered grid, right? I plus 3 by 2 j. this I plus half, next grid point is I plus 3 by 2, right? Clear?
Yes,
Yes,
sir.
sir.
Okay. So I minus half is also defined. This is I plus half. Next one is I minus half. Back one is I minus. So all these are defined. So these are known, right? These are known. So you can obtain U square value at these grid points. P plus 1 level, P plus 1 level. So this one is fine. So we have understood, and that means these variables at these grid points are defined. Now let us start with del u by del y. So del u by del y at P plus 1 level I plus half j. If you apply central difference scheme, that is uv P plus 1 I plus half j plus 1, uv P plus 1 minus I plus half j minus 1 by 2 delta y. Fine. That means u P plus 1 I plus half j plus 1, v P plus 1 I plus half j plus 1 minus u P plus 1 I plus half j minus 1, v P plus 1 I plus half j minus 1. Okay. Now tell me, out of this uv at these grid points, what are the variables that are defined at the grid points, and the variables that are not defined at the grid points?
Sir,
Uh,
V is
Yeah.
defined at the grid points. U is
Which
not
one?
defined. V is
Huh?
defined at the grid points.
V
V is defined at the grid points.
is defined, or u? Well, let us examine it for more clarity. Let me show you in paint. Okay, then it will be more clearer to you people. So these are the grid points. Okay, this is your, let us say this is your I plus half j. This is I minus half j. This is I plus 3 by 2 j, and this one is I plus half. What is that? I plus 1? This point?
J plus 1.
J
Very
plus 1,
good.
yes, sir.
J plus 1. And this point is
It's I plus half J minus 1.
yes, I plus half j minus 1. Okay. So at this point is V I j plus half. This point is I j plus 3 by 2, right? And this point is I j minus half. Fine? Clear? So these are the all defined points. These are the points where V is defined. These are the points where U is defined. These are the U points. These are the V points. V points. Now let us check one by one. So U I plus half j plus 1. Is that defined? I plus half j plus 1? Yes? What is the first term? U I plus half j plus 1?
So the
Yes?
first time is defined.
First term is defined. This is defined then. I plus half j plus 1. What about the second term? I plus half j plus 1. V. V I plus half j plus 1. Is that defined?
No,
No,
sir,
sir.
V is not defined. As
I,
V actually we define in the horizontal lines, and
yes, yes.
here.
This is the V line. This is the V line. This is the V line. And this is the U line. So V is not defined, right?
Yes, sir.
V is not defined because V at grid point I plus half j plus 1. Is there any grid point for V I plus half j plus 1? No, right? But we want to calculate the value of v at I plus half j plus 1, this point. How to calculate? Subhajit? How to calculate v? You are giving a very correct answer. In the last question that I asked, you are trying to give a very correct answer. Can you explain? How to calculate v at I plus half j plus 1?
So interpolate.
Interpolate. Yes. How you can interpolate? So v, that means v I plus half j plus 1. What will be the value of v a plus 1 j plus 1? Here, because I want to value of v at these grid points, not at the grid point, right? How to interpolate? How?
Sir, can I ask a question?
Yes.
Sir, I didn't understand that part. Why is v I mean, I plus half j plus sorry, what is it? I plus half j plus 1 not available at that
What are
at grid point?
what are the values of what is the staggered grid? Staggered grids means v grid. These are the v grid points. These are the v grid points. These are the grid points for the v, and these are the grid points for u. So u is only defined at these grid points. U is not defined at the grid points, and whereas v is defined at this grid point, but u is not defined at this grid points. Is that clear?
Okay, sir. Yes, sir.
Now
So
tell me,
at that grid point only u component is available to me. The
v component is not available. But we would like to have the component of v I plus half j plus 1. How to calculate?
Okay, sir.
V I plus 1 j plus 1. How to calculate? Somebody was telling interpolation. Somebody was telling it is correct answer. So how to interpolate?
So some interpolation schemes linearly support.
Same in very simple interpolation scheme. There is nothing difficult actually. Straightforward interpolation scheme you can apply. How we can apply? Now let us check this velocity. Okay, this velocity is a summation of velocity at this point and at this point by 2. Right? If it is suppose it is if this point is this point is equal to velocity at this point v is summation of this point and this point by 2. Suppose this is one p point and this is p1 point, that is this is equal to vp plus vp1 by 2. Clear? Clear or not? I am doing interpolation.
Yes, sir.
So this point is basically summation of this point plus this point by 2. If this is p point, this is p1 point, this is p1, that is vp plus vp1 by 2. Okay, vp plus vp1 by 2. So what is vp? Vp is basically velocity this plus velocity this by 2. That is vp equal to v I j plus 3 by 2 plus v I plus I j plus 3 by 2 this point, and this point is what is that? What is this point?
I plus 1 j plus 3 by 2.
I plus 1. Very good. J plus 3 by 2 by 2. Clear? Similarly, what about vp1? What about vp1? Equal to v I j plus half plus v I plus 1 j plus half by 2. So you know vp, you know vp1, you can calculate v I plus half j plus 1. Clear to everybody?
Yes, sir.
Very simple interpolation. Just by common sense you can do it. Any doubt? Let me know if you have any doubt. This is an exam type question. In examination I will ask. You have to show the variable values at all the grid points where it is defined. So if you have any doubt, please ask me. Is that clear?
Yes, sir.
Okay, good. Since it is clear now, so I have written similar thing. So same thing actually I have written. So I've just done only one linear interpolation, that is vi plus half and j plus 1 point, vi plus half j plus 1 point, that is equal to vi plus half j plus half plus vi plus half j plus 3 by 2, and vi plus half j plus 1 half equal to vi j plus half plus vi plus 1 j plus by 2. So basically I have done only for one. So for the other grid points, vi plus half j minus 1, you can do it by yourself. It's very simple. Same thing actually I have explained in the paint. So same thing, whatever I have explained, you can just try it by your home. At your home, you can do it. It's very simple, straightforward. Simply by linear interpolation, you can calculate the velocity values where it is not defined. So similarly, j minus 1 is defined, I plus half j minus 1 is defined, plus I plus half j minus 1 velocity value is not defined, because this velocity value at this grid point, I plus half j minus 1, that is I plus half j minus 1, this grid point v is not defined. So to calculate the v at this grid point, you need to again do the interpolation. Vi plus half j minus 1 equal to this point plus that grid point by 2. This point plus this point by 2, and this point equal to this plus this by 2, and this point equal to this plus this by 2. Simple linear interpolation, you can calculate the velocity values at these grid points. Okay. Now the pressure will be at ij point. Pressure will be at ij point. So there is a mistake here. It should be at ij point. It should not be I plus half j point. It will be at ij point. Okay. Pressure has to be calculated at the ij point. So that is del p star by del x. That is the Okay. Am I audible now? Actually, there is a call in between. Am I audible?
Yes, sir.
Okay. Okay. So I got a call and my phone got disconnected. Can you see the screen now?
Yes, sir.
Okay. 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 So P has to be discretized at ij grid point, right, Tisha? So that means we can simply pi plus 1j minus pij by delta x. If you want to do central difference, you can do a central difference also. Here I have just done only forward difference. I plus 1j minus pij by delta x. Okay, this is very simple. Now what will happen for the division term? Del 2u by del x2 plus del 2u by del y2 p plus 1 I plus half j. That is, we can write it as del 2u by del x2 p plus 1 I plus half j plus del 2u by del y2 p plus 1 by I plus half j. So what is del 2u by del x2? P plus 1 I plus half I plus 1 I plus half plus 1j minus 2 p plus 1 I plus 1j plus 2 plus p plus 1 I plus half minus 1j. That is a simple central differences formula. That is ui plus 1 minus 2 ui plus ui minus 1 by delta x square. That's why I have written here u I plus half plus 1j minus 2 u I plus half j plus u I plus half minus 1j by delta x square. That means I plus 3 by 2j minus u I plus half j plus ui minus j. Please see that all the values of these variables are defined at this grid point. So I plus 3 by 2 j u, it is available. I plus half j u, it is also available. Similarly, I minus half j u is also available. Now let us see for the other term, del 2 u by del y2 p plus 1 I plus half j, that is u p plus 1 I plus half j plus 1 minus u p plus 1 I plus half j plus u p plus 1 I plus half j minus 1. So here also you can see I plus half j plus 1 is defined. I plus half j is also defined, and u I plus half j minus 1 is also defined. So if you can see, very interesting thing from the discretization at the staggered grid points, you can see the diffusion term. If you discretize the diffusion terms, the discretized equation arising out after discretizing the diffusion term are available at all the grid points. That is, these grid point values are available. Whereas you need to apply the interpolations, linear interpolation scheme for the convection term. That is a convection term. This is a u dl u dl x plus v dl y is a convection term. You need to apply linear interpolation for the convection grid points, for the convection term for the grid points where the variable values are not defined. Primarily here v is a variable where it is not defined at the I plus half j plus 1 grid points. So accordingly, you need to apply linear interpolation scheme for the variable values at while discretizing the convection terms of the momentum equation. Similarly, you can also apply similar kind of discretization scheme at the staggered grid points for the v momentum correction equation. Predictor equation. So v momentum predictor equation, you can also apply the similar kind of discretization scheme while discretizing the v momentum predictor equation at the staggered grid points. Is that clear to everybody? Any question? Any question?
No, sir.
Okay. Very straightforward.
Sir, why the pressure distribution is done by the forward difference scheme only?
No, if I have just written forward difference, if you want to apply a center difference, you can also apply center difference.
Okay, sir.
Okay, just to give an example, I have shown here as a forward difference scheme. Okay. Okay, so next slide. Now pressure correction equation, because we have again pressure correction equation that has to be solved for the momentum equation calculations, numerical calculation for the momentum equation. So that is, what is the pressure correction equation? Del 2 p prime del x2 plus del 2 p prime del y2 at p plus 1 level equal to rho by delta t del u star by del x plus del v star by del y. This is a Poisson equation for the pressure correction that already we have defined in the last class. So this will be at ij grid points, that is p prime I plus 1j minus 2 p prime ij plus p prime I minus 1j by delta x square at p plus 1 level, plus this term P prime ij plus 1 minus 2 P prime ij plus P prime ij minus 1 by delta y square at P plus 1 level equal to rho by delta t, whether P is defined as the ij grid point, but U star and V star at I plus half and j plus half j, I plus half j and ij plus 1 j plus half grid points. So here you need to discretize this U star x, del U star x, del x and del V star del y at I plus half for the U moment for the U grid point and the V grid points. You need to discretize using the staggered grid technique. That is del U star by del x. If we apply central differential scheme, that will be U I plus 3 by 2 j, already I have shown, minus U star I minus half j by 2 delta x plus rho by delta t, this term V star I j plus 3 by 2 minus V star I j minus half by 2 delta y. Okay, clear? This relation is clear? Or if you have any question? Do you have any question?
No, sir.
Okay, this is straightforward discretization. Okay, so here you can see you are discretizing this special correction equation, and here you know the U star V star because already these values are obtained from the predicted equation. So this part is known. Now you can easily solve this special correction equation to obtain the values of P prime. Once you obtain the values of P prime, then you go ahead in calculating the velocity correction equation. What is the velocity correction equation? You have obtained U P plus 1, there is a corrected velocity equal to U star minus delta t by rho del P prime del x. Right? Is
Yes,
that okay?
sir.
Okay, so we have derived the last class. So that means U star. So if you discretize this equation, that will be U P plus 1 at I plus half j equal to U star I plus half j, because you are discretizing at I plus half j grid points, minus delta t by rho P I plus 1 j prime minus P I prime I j by delta x. So I have just discretizing it as a forward difference. If you want to do discretization by center difference, you can also do. But here I have given as a forward difference. Is I plus half j P prime minus P prime I j by delta x at P plus 1 level. Okay, any question on this slide? Do you have any question on this slide?
No, sir.
Is clear to everybody?
Yes, sir.
Is it clear to everybody? Okay, okay. Now you have got sets of discretization equation. So in order to solve the equation, what do you need? The boundary condition. So what will be the boundary condition? At the walls, no slip boundary condition. You simply put U equal to 0. No slip means velocity components are 0. So at the walls, you have a no slip boundary condition. So no slip boundary condition for the velocity will be equal to the no slip boundary condition for the correction equations also, U star and V star. So U is equal to 0 at the wall. U star is also equal to 0 at the wall. V equal to 0 at the wall. V star will be also equal to 0 at the wall. This is called a no slip boundary condition. Velocity component at the wall will be 0. What about the pressure? At the wall, please remember this. At the wall, pressure boundary condition is always given as the Neumann boundary condition. That is del P del N equal to 0. Similarly, if del P del N is equal to 0, for the pressure correction equation, you have to also apply the Neumann boundary condition. That is del P prime by del N is also equal to 0. Okay. At the wall, you have no slip boundary conditions for the velocity. That is E equal to 0, V equal to 0. If E equal to 0, V equal to 0 at the wall, similarly, you have to also prescribe U star equal to 0, V star equal to 0. That means predicted values of velocities also will be equal to 0 at the wall. Basically, predicted values of the velocity will be also satisfy the no slip boundary condition at the wall. For the pressure, you have to apply the Neumann boundary condition. That is del P del N equal to 0. And for the correction equation, that is also be the del P del N, del P prime del N equal to 0. So at the wall, you have to apply Neumann boundary condition. For the pressure, del P del N equal to 0, or it is the surface normal. And for the pressure correction, del P prime del N is also will be equal to 0 at the wall, where it is the surface normal. What about the inlet? What about the outlet? Outlet will have a fully developed boundary condition. What about the outlet? Outlet is a fully developed boundary condition. So how we can apply the fully developed boundary condition? So fully developed boundary condition is basically del u del n equal to 0. At the outlet, for the velocity, del u del n equal to 0. And for the velocity also del u del n equal to 0. It is a surface normal. This is basically called the fully developed boundary condition. So at the outlet, if outlet is at the x direction, it will be del u del x equal to 0, del v del x equal to 0. If outlet is at the y direction, it will be del u del y equal to 0, del v del y equal to 0. That's why I have written as at the outlet, if boundary condition is always at the fully developed boundary condition, and for which the boundary condition for the velocities are del u del n equal to 0 and del v del n equal to 0. Basically, these are the fully developed boundary conditions. What about the pressure? At the outlet, if you specify the pressure value, that means at the outlet, if you have a atmospheric pressure, if the pressure is atmospheric, that is P equal to 0. If we specify the pressure value, then pressure is already known, that means correction is 0, that is P prime equal to 0. At the outlet, if the pressure is atmospheric pressure, so that outlet atmospheric pressure has to be satisfied. Pressure is specified at the outlet. If pressure is specified, so there is no correction needed on the pressure. That means pressure prime is always 0 at the outlet. Any doubt on these boundary conditions?
No.
Any doubts?
Oh wow! I like Christmas Eve.
These are very important boundary condition you will be requiring while solving this Navier-Stokes equations using simple algorithm.
Sir, outlet boundary condition. Once again, repeat again.
Okay. Yes. Okay. Let me show you here. So suppose this is your domain. This is your domain. This is your inlet. This is your outlet. Okay. Suppose this is your x direction. This is your y direction. Fluid is entering in and fluid is going out from this domain. So at the outlet, boundary condition is fully developed boundary condition. Fully developed boundary condition means, if since this is the x direction, that means del u del x equal to 0, del v del x equal to 0, and pressure, if pressure outlet is pressure is atmospheric pressure, then pressure equal to 0. That means pressure is specified. If pressure is specified, that means P is already known. If P is known, you do not need any correction to the P, right? That means P prime is 0 at the outlet. Okay. For a situation when outlet is at the x direction, if we have some different situation, for example, if we have this kind of this domain, fluid is flowing in here. This is the inlet, and this is your outlet. Okay, so this is your x direction and this is your y direction. So at the outlet, you will have is always fully developed boundary condition. Fully developed boundary condition. That means del u, since this is the y direction, del u del y equal to 0, del v del y equal to 0. Now also you have pressure is specified. The pressure will be atmospheric pressure, so it is 0 here. Gas pressure is 0. If gas pressure is 0, that means you do not need any correction to the pressure. That means P prime is always 0. So in general, we can write at the outlet, fully developed boundary condition has to be specified at the outlet. That means del u del n equal to 0. Del u del n equal to 0. where n is the surface normal, that means either n is x or n is y, depending upon the outlet surface normal. And del v del n equal to 0. And p is always specified. So p is specified. P is specified. So either it is 0 or some value you are specifying. See, in general it is 0. For example, if it is satisfying the atmospheric boundary condition, if p is 0, that means p prime will be automatically 0 because p is specified, p is already known, so you do not need any correction to the pressure. Is that now clear?
Yes, sir. Clear, sir.
Okay, okay. So now we know what are the boundary conditions that you will be requiring while solving those discretized equation using the simple algorithm. Okay. So in a nutshell, similarly, also you can discretize velocity correction equation for the v, that is vp plus 1 equal to v star minus del t by rho, del p prime by del y, p plus 1. Similarly, you also can discretize for the v momentum equation like we have discretized for the v momentum equation, v momentum predictor equation. So in a nutshell, what is the flow chart for the simple algorithm? Whom to ask? I can also read it out. I want someone of you should read. Whom to ask? Whom to ask? Whom to ask? Yeah. Subhajit. Subhajit, are you there?
Yes, sir.
Okay. So let us start reading the simple algorithm.
So step 1, initialize velocity as staggered grid point, guess P star at the grid point.
What does it mean? What does it mean?
Staggered. U star, V star, and P star. This the U star and V star the predicted velocity, and P star is the guess velocity.
That means initialize. You have to initialize. Please remember, in the CFD calculation, you have to initialize the velocity values, right? Initially, you have to initialize all those velocity values and pressure values. U star, V star, and P star at grid points. So initially, what is the initial condition? Initial condition has to be specified. That means U star, V star, and P star value has to be specified as 0. Okay.
Yes, sir.
Now on step number 2. Subhajit, you can mute yourself. Or no, step number 2. Or no, are you there? Or no? Okay. No, they are not there. Don't do it. Trishul. Step number 2.
Yes, sir. First inner loop solve velocity. Yes, sir. First inner loop solve velocity prediction equation with boundary condition for U star and V star till convergence.
Okay. Second inner and next one is
Second inner loop solve pressure correction equation with boundary condition for P dash with the predicted velocities till convergence.
okay. So Simna, tell me what does it mean?
Sir, as we have calculated the U star and V star, then from the pressure correction equation, we can get the P prime value.
No, that is fine. Basically, I wanted to ask you that what does it mean? What do you mean by first inner loop and second inner loop? What does it mean?
Sir, we have to check convergence
Yes.
so that we get the value of U star and V star.
Yes, that is true. Similarly for the pressure prime, P prime equation, right?
Yes, sir.
That is called second inner loop. That means you can, if you just go back, this is very important thing. You just go back. That is, you have two equations, right? One is U star equation, one is V star equation. So this equation has to be iterated till convergence because this is an implicit equation, right? This equation and this equation number 1 and equation number 2 are to be iterated till convergence to obtain U star and V star value. That is called the first inner loop. Okay, once you have obtained convergence at a particular time step t, you have to iterate these two equations till convergence to obtain u star and v star. Okay, once you obtain u star and v star, then you have to go to the pressure equation, that is this equation. This equation. No, this equation. So this equation is also pressure correction equation. This is two-dimensional pressure Poisson equation. So this equation has to be also iterated till convergence to obtain P prime. Clear? That is called the second inner loop.
Yes, sir. That means at each time step value, we have to check the convergence for P prime.
Yes, yes. You have to check the convergence for the pressure and U star V star. P prime and U star V star till convergence. Okay. So once it is done, then what you have to do? Chodadeep, what you have to do?
Then we have to correct the velocity from the velocity corrector equation.
Okay.
And
What is
then
that?
go back. U p plus 1 equal to E U star minus del T by rho del P del X at the current time step P plus 1. Similarly for the V P plus 1 equal to V star minus del T by rho del P del Y at the current step. Then we have to check for the convergence of the velocity corrector equation and then go to the next time step.
Exactly. So once we have done all these steps, because no, that is not that. Because basically you have to take convergence of the velocity correction predicted equation for the first inner loop, second inner loop, predicted equation for the convergence. Okay, there is no convergence for the corrected equation. This is basically
Means the velocity corrector equation is satisfying the continuity. Again, this velocity will not satisfy the momentum. We have to again go back to the momentum equation and then repeat the step.
Right.
Right.
That is right. Or also you can check whether divergent of U star is closer to 0. That is divergence of U star less than epsilon. That means these predicted velocities are satisfying the continuity or not. Okay. That means divergence of U star, what does it mean? That is del U star by del X plus del V star by del Y. Right? There is a continuity equation. So the one of the important criteria of the simple algorithm that while solving it numerically, you need to check continuously whether the continuity is satisfying or not. That means you need to solve the governing equation in a way that you should continuously satisfy the continuity. That is, grad of divergent of U star should be equal to 0 or closer to 0. That's why you have to check. Once you have done all these calculations, then you have to check whether divergent of U star is less than or equal to epsilon or not. That is epsilon 10 to the power minus 7 or 10 to the power minus 8, some convergence criteria. Whether after performing all these calculations, whether this is, after that you have to calculate divergent of U star, that is del U star by del X plus del V star by del Y, and you have to check whether del U star by del X plus del V star by del Y is closer to 10 to the power minus 8 or 10 to the power minus 7 or not. If it is yes, if it is no, then again you have to go back to step 2 and repeat these calculations. You have to go back to step 2 and you have to substitute U star equal to UP plus 1, V star equal to VP plus 1, and P star equal to P plus 1, and again perform these calculations. And again you have to check this divergent of U star equal less than equal to epsilon or not. If it is satisfied, then you have to go back to the next time step. Then you have to proceed to the next time step. Sorry, not go back. You have to proceed to the next time step, t equal to t plus delta t, and perform the next level of iterations. Basically, this is a simple algorithm. Is that clear to everybody? Any doubt?
No, sir.
Huh? No or
No
yes?
doubts.
No doubt?
No, sir.
Sir,
Sure. Yes.
sir, then we are first of all we are calculating the variable value first. We are guess value. There is a guess value. We have initialized the guess value, and then after that there are the equations. We are solving them, and then we are updating the u p plus 1 value with the guess with the
We're not updating. We're correcting.
correcting the u p plus 1 value. I mean and then again the guess value will be calculated in the next iteration, and until the guess value satisfies the continuity equation, right?
Yes, that is not a guess value. It is called the predictor value. You should not tell
Yeah,
guess.
predictor value. Yes, sir.
Yeah, predictor value is on satisfying continuity. If you satisfy the continuity, then you have to go to the next time step. Otherwise, you have to keep on iterating these loops.
If it is satisfying the continuity equation, then we will go to the next time step.
Then you have to go to the next time step.
Okay.
Okay.
And what is the convergence criteria for the time step? I mean, when will we
No,
stop
if
there?
you want to check the steady state, that is up plus 1 minus up plus 2 is less than 10 to the minus 3 or 10 to the minus 4, then you have to stop the calculation. That is, you have these are steady state.
Okay. Yeah. Yes, sir.
Okay. Any doubt? Do anybody have any doubt? Yes or no? Is it clear to everybody? Ayan Pacha.
আমার ড্রেসটা তো আরো নোংরা করে দিচ্ছে মা এটা আমরা
Ayan Pacha, are you there or no?
কিছু না তো আমরা যখন হোটেল থেকে আসছিলাম তখনই তো নোংরা
No. Okay.
কেমন মিট্টির মতো
Vishul?
Yes, sir. Sir, no doubt.
No doubt? Okay, so clear? Everything clear? Okay.
মাম্মা এটা নোংরা করে আছে
Okay, very good. This is the last slide of your CFD course. Thank you.
ঝাড়ুটা কোথায় ঝাড়ুটা পেয়েছি
Sir, one thing.
Yes.
Sir, could you repeat the criteria for steady state in that algorithm?
Steady state criteria, right? Okay.
Yes, sir.
I'm